All right, hello. Welcome to whatever week this is. I don't know. Time has no meaning. Um, Today we're going to look at chemical reactions and chemical equations. I've got a nice blank sheet of notes here because we're going to kind of go through it together now, and then we'll have the usual practice stuff later. I didn't think it really made sense to just have a whole big block of text here explaining something that is it's easier for me to just show it to you and really not that difficult, especially compared to the stuff we've been doing the last couple of weeks, which I would say is pretty difficult stuff. Okay, so chemical reactions are we've already talked about them. Chemical changes, when there's a chemical change where atoms in a molecule are rearranged, or in any kind of compound are rearranged with others to make a new kind of a substance. What we're going to talk about specifically now is how to represent those reactions on paper. And when we write a chemical reaction down on paper, what we're writing is a chemical equation. And you've probably seen some of these before. So I'm going to write one down, and then we're going to talk about the different parts of it and some of the issues and why we have to do this thing called balancing. So here is a chemical equation. That shows the reaction of hydrogen gas with oxygen gas. So you'll remember from a few chapters ago now that some of the elements in the periodic table don't just exist as individual atoms, or they're not expressed as individual atoms. They're what we call dimers. They have two atoms bound together. So hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine are always two. So here's a molecule of hydrogen, molecule of oxygen, and we're saying that these things combine to make water. Some other information that's here is these little G's in parentheses. Those indicate that we are talking about the gas state of each of these. So we'll talk a little bit about the different states as we see some more reactions. And there's a problem with the way that I've written this reaction. And if you look at it for a little bit, you might see that problem. If it's obvious to you, you want to post it in the chat, go ahead and do so. If it's not, that's okay. We're going to talk about it. So one thing we can do to help make obvious the problem with this chemical equation is look at the Lewis structures for these molecules. So let's draw some Lewis structures. Hydrogen's going to look like this. Oxygen's Lewis structure looks like this. Yeah, exactly. Both of you, I think both of you got it. There's two oxygens in the reactants and not in the products. So let's see why that's a problem. Here's our Lewis structures here, and then here's a Lewis structure right there. Okay, so when you look at the structures here, what you can see is that, imagine that you're actually doing this physically, like you've got a model and you're building models of hydrogen and oxygen. And then to make the water, what you have to do is you have to pull apart the hydrogen, pull apart the oxygen, and kind of rearrange these. But as you noticed, if you did that, you'd be left with an extra atom. And that's not okay. We have a law of conservation of matter, which says that in a chemical reaction, matter can't be created or destroyed. So an atom can't just disappear. That's not right. So let's look at some of the options we have for fixing that. And there's really only one correct one, but we'll talk about a couple common mistakes first. So one common mistake is to say, well, okay, how about instead of water, we just add that there's an extra oxygen atom here. So maybe we just, we're doing our accounting of the reaction and we forgot an oxygen atom, so we just stick it on there. That doesn't work. And the reason that doesn't work is because remember this equation is depicting a known chemical reaction. We can actually physically do this and see what we get. And if we don't get any extra oxygen atoms, then we won't see them. And that means they're not there. So we can't just add them in on paper if the reaction's telling us they're not actually there. So that doesn't work. Another option here might be to have to change the subscript here. So instead of H2O, we have H2O2. Now that works. This is also a problem because we no longer have water. I don't know if you know this compound H2O2. It is hydrogen peroxide, and hydrogen peroxide is not the same as water. Don't drink it, right? So we definitely can't do that because this is describing a different process. If hydrogen and oxygen combine to make hydrogen peroxide, then this would make sense. But we're saying that's not what happened. That's not what happens. So, so we can't do that. So what that means then is we can't just add the extra atom to either side that's missing. What the real problem is here is that hydrogen and oxygen do not react in a 1-to-1 ratio. So we can't just take one hydrogen molecule and one oxygen molecule and then make one water molecule. That's just not how this reaction works. We have to react these things in such a way, in such a ratio, that we account for this difference. So for this, in this case, the solution is to react 2 hydrogen molecules with the oxygen molecule and then form 2 water molecules. And so now that shows the actual full accounting of this reaction, because now we have 4 hydrogens on the left, 4 on the right, 2 on the left, 2 on the right. 2 oxygen on the left, 2 oxygen on the right. So now it all works out. We didn't change anything about the subscripts, the compounds. We didn't add any extra things, but we did say there's a different ratio here for the reaction. And the way we express that ratio correctly is with large numbers in front of or to the left of the molecule. So we would say 2H2 plus 1O2. When it's just 1, we just leave it off. So that's where there's nothing written here, but that means there's just 1. And then 2 here. So that represents these 2 molecules. That represents these 2 molecules. And then this should be a 1 representing these molecules. All right. So now that that's taken care of, let's talk about some more of the terminology or the way we describe these things. So usually on the left side, whatever kinds of compounds are on the left side are called the reactants or sometimes reagents. And then whatever's on the right side are the products. Now later in this chapter, we'll see that reactions actually can go back and forth. So it's not always left to right, but this is often how we will refer to them as the reactants on the left and the products on the right. I got rid of my state things here. We'll add that back in. These things are called the state. Of course, we already know about states. Sorry, I know my head's in the way there. So we've got G for gas, S for solid, L for liquid, and then there's one more that you may not have seen before, and that is AQ, which stands for aqueous, which means in solution, or we'll say dissolved in water. So in some of these reactions, you'll see AQ. Now, the states, they'll often be given, but if they aren't, you won't necessarily know them. So when we get into actually writing some equations later, we'll often leave the states off just because we don't necessarily know what they are in that particular reaction. That's fine for now. All right, and then the other thing you should know is just that these numbers are referred to as the coefficients. And that's what we'll use to do what we call balancing the equation, making sure that the ratios are correct so that the left and the right side have the same numbers of atoms. All right. So let's get into some of these reactions now and talk about what happens when we encounter an equation or we're writing down an equation. And we want to make sure that it is balanced. And when we say balanced, we mean the same numbers of atoms on the left and on the right. So let's take this one here, and we're going to rewrite it and kind of go through it a little bit more slowly here before we. So we've got potassium chlorate decomposing into potassium chloride and oxygen. And I believe this would go solid gas, but the states aren't given, so we'll just leave them like that. So in our example here, I just said, oh, well, we'll just add another hydrogen and add another water, and then it'll all work out. And that's fine for very, very simple reactions, very, very simple equations when you can do that. But in many cases, it gets more complicated. So we're going to look at a systematic way where you can say, all right, here's my equation. Here are the things I have to do to make sure it gets balanced. So the first step is to just count up your atoms on each side. So I've got this equation here, and I'm going to count up on the left. I've got 1 potassium, 1 Cl, and 3 O, 3 oxygens. See how I do that? Separate all the atoms out as though you were pulling apart a model and count how many of each type you have. So then on the right, I'm going to do the same thing, and I'm going to include all of these together. So I've got 1 K, 1 Cl, and 2 O. All right. So now I can look at those, and it doesn't matter what order you write them down in. I just wrote them down in the order that they were present in the reaction there, in the equation formulas. We write them down, and we can look at them and decide, is it balanced, is it not? And I think you can see that this means it is not balanced. The potassiums are balanced, the chlorines are balanced, the oxygens are not. There are more on the left than there are on the right. So then we have to say, how can we add coefficients to bring these into balance? And in this particular equation, it's not as simple as what we did before. We can't just say, oh, let's add a 2 here, because that's going to give us 4, right? And that's not 3 either. That's still not balanced. So we have to be a little bit smarter about this. We're going to do something to those oxygens, but we can't just add another one. It's not that simple. So we look at the 2 and we say, all right, what coefficient could we put in front of any of these, or multiple coefficients, to make those oxygen numbers equivalent? The answer is you would need to put a 3 here, and you need to put a 2 here, kind of like when we build those molecular or the compound formulas. We need to balance them out, right? Same idea. If we do this, and here's an important next step, we need to correct our numbers. We need to change the numbers the same way that we changed the coefficient. So if we put a 2 here, there's no longer 1 potassium, there are now 2. There's no longer 1 Cl, there are 2. And there's no longer 3 oxygens, there are 6. And then on the right side, we only changed the oxygen numbers. So instead of 2, there are now 6, because we've got 3 molecules with 2 each, so that's 6 overall. So we did it. We brought the oxygens into balance. But in doing so, we threw off the potassium and the chlorine balance. And that's okay. That happens when you're balancing the equations. You'll have to go through the different atoms, sometimes multiple times, going back and forth until you get them balanced. There's some trial and error here. And if it's not working, sometimes you can go back to the beginning and try again with different numbers and play with it a little bit. It's not always going to be right with your first numbers. All right, so what we can do then is we can look at these and say, well, how do if I've got 2K on this side and 1 on this side, I need to get 2 on both sides. So I'm going to put a 2 here. Notice I say put a 2 here. I don't say add 2, because we're not adding 2 more because there was already 1. We're putting a 2 there so that there are 2 total. So now we correct our numbers again. We've got 2 and 2, and then we're good. We're balanced. Then I always like to take one last look at the coefficients and see, are there any common divisors? Did I inadvertently, the process of balancing, did my numbers get too big and I could actually reduce them, like by dividing them each by dividing all the numbers, all the coefficients by half, or by 2 or by 3 or something? And I look at them and you can see that they have no common divisors. So that's right. So that's my balanced equation. The other nice thing about balancing equations as an activity, as a quiz or test question, is you can always check if you're right or not. If you've got the right formulas and you've got the right number of atoms on both sides, or the same number on both sides, then your equation is balanced. That's it. So you can always check your work and you can always tell if it's balanced or not. All right, let's try this one here. If you're following along, I'm going to pause for a minute and give you a chance to try it. So we're going to do the same thing. You're going to total up the atoms on the reactant side and the product side, and then try to adjust the coefficients one by one so that you get them balanced out. Go ahead and give that a try. So if you're following along right now, keep doing what you're doing. I'm going to start filling in some of these numbers. Just don't look up at your screen until you're done. And then and I'll try not to talk until I've put the numbers in, and then we'll talk about it. And hopefully you have your numbers in as well. All right, did you get those? Hopefully. So I added up the totals, and then I started with sodium, and I said, okay, there's 2 on the left and 1 on the right. So then I put a 2 here, so there could be 2 on the left and 2 on the right. That also changed my CL, which notice originally was already balanced. So don't be afraid to wreck your previous balancing when that happens. That's just how it goes. I changed the CL, so then that was the next one I looked at. I saw that I had changed that, so I then changed the left as well, put the 2 there. That affected my H and my CL, and yeah, then it all worked. So these other blanks where we didn't put anything, remember that those are actually ones. When you don't have a coefficient, a number showing there, those represent 1. So that's our balanced equation, and we know that it's balanced because we can always add it back up again, make sure that it stays, that everything has the same number on both sides. All right. So there's lots of different ones here for you to practice. I want to go through a couple hints here. So these other ones are for practice for you. I don't know if you can read these. It might be small on your screen, but I'll talk about them. But as these things get a little bit more complicated, just some things to keep in mind. So first, only change the coefficients. That's all we're ever doing is changing those numbers out front. We can't change the subscripts at all. In general, you want to do the compounds first and then the lone elements last, because when you change the number of a lone element, you don't affect anything else. But more importantly, this second sentence, if an element is in more than one compound on the same side, save it for later. So going back to, I don't think we had that in either of our examples here. Well, we did, but it was already balanced, so we didn't have to worry about it. But let's look at one of those examples if we could. I'm not sure there's one actually here. Here's one. I'm going to rewrite it here. So this is combustion of butane. Butane gas reacts with oxygen gas to make carbon dioxide gas and water vapor. This one's actually going to run. We're going to run into two problems here potentially. So we'll do this. We'll go through this one together. All right. So first, we're going to add up our stuff, our atoms. This side's got 4C, 10H, 2O, and this side's got 1C, 2H, and 3O. All right. So that second hint, what that's saying is if an atom or an element is in more than one compound on the same side, save it for later. And in this case, we're talking about oxygen. So we've got 2 on this side and 3 on this side. And there are so many different ways that we could balance that. So we definitely have to bump this one up to 4, but then we could like add a second one here. Or we could go up to 6 here and then have 2 here and 2 here. Like there's just too many different possible combinations. And so what that tells you is you want to get the other stuff kind of locked into place before you start messing with that, because you could end up with other numbers that don't work for the other atoms. So we're going to leave the oxygen till last because it's in more than one molecule or more than one compound. We'll start with the carbon here. It doesn't matter if we start carbon or a hydrogen. Either one would be fine because they're only in one compound on each side. So we see 4 carbons here, 1 here. We put a 4 here, and that changes us from 1 carbon to 4 and from 3 oxygen to 12. So you can see we're already really messing with the oxygen a lot. So good thing we didn't try to balance that right away. All right, now we can go to the hydrogen. We've got 10 on the left, 2 on the right. So we need to put a 5 here so that we have a 10 total on this side. That's also changing our oxygen number again. So now we don't have 12, we have 8 plus, oh, we didn't have 12 before either, did we? We had 11. Or no, we had 9. Yeah, 4 times 2 is 8, plus 1 was 9. So now we don't have 9, we have 13. 8 plus 1, or plus 5 is 13. Okay, I'm sorry, I said a lot of wrong things. I hope that wasn't too terribly confusing. We put the 5 here, we've got 10 hydrogens and 13 oxygens total on this side. Okay, so now we jump over to the other side. We've got a lone element oxygen, so we can balance it. 13 on this side, 2 over here. So what number do we put here so that we have 13? And here's where we run into another problem, right? Because there is no number we can put here, no whole number anyway, to get 13 because we have to multiply it by 2. So we could put 6.5, but that's not an okay coefficient to use. We want to use nice whole numbers. So we're stuck. We've got an odd number on the left, and we can only do even numbers on the right. So the solution here is actually another hint from up here. Oh, where'd it go? Number 5, coefficients should be whole numbers. To get rid of a fraction, multiply the whole equation by a whole number, like 2. So if we double everything, we keep all the other atoms all still in alignment or in balance. We only change, and we're actually going to just forget about the oxygen for a minute. So let me show you what that looks like. We're going to change this from a 1 to a 2, which gives us 8 carbons and 20 hydrogens. Then we're going to change this one from a 4 to an 8. And if you're doing this on paper with a pencil, you could erase. I'm just doing cross out so you can see all the steps here. That's going to change us and give us 8 carbon and, well, we know it's going to be more oxygen. We'll get to that in a second. And then I'm going to change this one to 10. So I've just doubled everything. And my total number of oxygen now is 16 plus 10, which is 26. And that's a pretty big number, but it's now an even number. So if we jump back over to the other side, we can say what times 2 is 26? Well, 13 times 2 is 26. And now we've got 8 carbons, 20 hydrogens. Sorry, I forgot to update that one. 20 hydrogens and 26 oxygens on both sides. All right, so a couple issues there. One, make sure you save the atom that's in multiple compounds until last. Second, if you run into this even odd issue, you can always multiply everything by some number. And usually just multiplying by 2 does it. All right, so there's lots and lots of practice here for you. You will be able to try some of these with the counting tables here for you, and then a bunch where they're not there. So give those all a try. And then next time on Wednesday morning, we will talk about energy. I had a couple questions about the exam. We will be going through the exam on, I think we'll do it on Thursday. I wanted to wait until Group B gets all of their exams back on Wednesday. So once I give those back on Wednesday, then we can go through the exam on Thursday. All right, so happy balancing equations, and I will see half of you on lab. I'll see Group B on Wednesday, and the rest of you, hope everything is going okay. Let me know if you have any questions. Bye.